Welcome back. This is Mr. Wakefield looking at section 7.5 right now. The concept is rationalizing the denominator. And before I go into some additional details, I want to mention, as I pull up the another sheet here, just a minute. But what does the rationalizing the denominator mean? It means that we need to take the denominator and convert it to what? Let's take a look at that here. It says to convert the denominator to a monomial, just a regular term, not a radical term, but just a regular term with a whole number coefficient, with no radical though. Okay, in other words, not a radical term, no radical there, but just a regular term. You know, like something like 3x squared or 5x to the third or one of those things. Or it could even be just a constant without a variable like 6 or 8 or something. Okay, that's what we're looking for. The reason why it's not currently that way is because when you have a radical, such as radical 3, if you've got like a square root that doesn't have a perfect square number underneath it, like 4 or 9 or 16 or something like that, or if you've got a cube root that does not have a perfect cube underneath it, you know, like 8 or 27 or 64, one of those numbers, then what happens is that's called an irrational number if it's a whole number, okay? It could be different if it's something else, but if it's a whole number like 1, 2, 3, 4, 5, one of those numbers, but it's not a perfect square or perfect cube number for a cube root, all right? It's called an irrational number. And an irrational number is when when you put in your calculator, and I'm not saying to do that here, okay? Don't do that here, all right? It'll give you an answer that's not exact, like we talked about back in 7.3. We don't want that here. But if you were to do that, just to make a point here that I'm trying to make, if you put square root of 3 in your calculator, it would be a decimal that covers your entire screen with no repeating pattern of any kind like some decimals have. And when you have a decimal that covers your entire screen with no repeating pattern, that typically means that it is a decimal that goes on forever. It's just that the decimal has to stop at the end of the calculator screen. But it typically means that it goes on forever with no repeating pattern at all, and that's called an irrational number. So as you can imagine, a rational number is the opposite of that. It's either a decimal that either ends, meaning it doesn't go on forever, like I just said, or it has one of those repeating patterns. Like, for example, if you put 1/3 in your 1 divided by 3 in your calculator, it would be 0.33333333, and the 3's just go on forever. That's a repeating pattern. Okay. So anyway, that's just a little explanation as to why these radicals are not rational numbers, and so we need to rationalize them, meaning we turn the denominator into a rational number. Okay, a whole number is a rational number, okay, even though it doesn't look like what it is defined here. It's like a smaller version of this, okay, because any whole number is like a small decimal. You just don't see the decimal point. So that's why I was saying a whole number coefficient in a normal monomial term with no radical will get the job done. Okay? And so how are we going to go about this here to make this happen? Well, before I get into that, you guys, I want to just go over something here that we're really going to need in this section. You don't have to write this down. You just take a look, although you're welcome to if you want. But we really need to talk about how to multiply not just a radical term times a radical term, which we already talked about, and we'll talk about it again here, but also what happens when you mix together radical terms with some regular terms like 4 or 3, okay, stuff like that. How do you multiply these things together? Well, we talked about this one already. Outside times outside stays outside. Inside times inside of the radical stays inside. In other words, the outside parts do their thing, the inside parts do their thing. Similar thing when you multiply regular terms. I put these side by side over here on the right hand side because I want you to see the connection between these problems on the left and these problems on the right. Okay, the outside part of the radical is similar to coefficients. It behaves in the same way. You know that we're supposed to multiply those together as well, and we also get 15. And then the variable parts of when you multiply regular terms together, the variable parts behave in a similar way as the inside of the radical. You multiply those together. Okay, so seeing that connection really helps us kind of tie all this together. Same thing here. You've got a regular term, which is the outside of a radical, times this radical term where 3 is outside the radical. So again, the outside parts are similar to the coefficients. What is this equal to over here? This is equal to 12x squared, isn't it? Okay, well, just like you do 4 times 3 here, you're going to do the outside parts over here to get 12, and then just like the x squared doesn't have another x to combine with it, we just bring the x squared on down, don't we, into the answer. And so it's the same thing here when you have a regular term 4 times a radical term. Since there's only one radical, the radical just drops on down into the answer just like the x squared did. Okay. What happens if you have a radical term times another radical term, but there's nothing in front of the radicals this time? That means that there's invisible ones in front of the radical. Just like with this problem here. You got invisible ones in front of these terms here. And so when all your coefficients, when both of your coefficients are equal to 1, you can kind of ignore that as long as you've got variables there as well, because 1 times 1 is 1, and the 1 is actually invisible sitting there when you write it like this. And so it kind of does it for you when the coefficients are both equal to 1. It gives you the correct coefficient down here without you having to do anything. It's just invisible, that's all. It's the same thing here. Okay, we know that when you have a radical term times a radical term from up here, that you multiply the outside parts. But if they're both equal to 1, then 1 times 1 is 1. But I don't need to write the 1 if I'm going to have a radical part next to it, because then the 1 can be invisible in front of it. So you just need to do the inside times the inside, just like I did up here. Okay, so you theoretically are doing 1 times 1 equal to 1. It's just that you don't need to write that 1 right there if there's something being multiplied by it. Okay, the 1 can always be invisible as long as you're multiplying it by something. Okay, that something you're multiplying by would then be the answer, and you can just write that down. And that's what I did here. The 1 can be invisible. When you have a coefficient times a term that has a variable but no visible coefficient in front of it, okay, which means it's equal to 1, okay, when it's written like that, doesn't this just smush together? Isn't this just 3x to the 4th? In the same way, if you have a regular term times just a radical with nothing in front of the radical, this also just smushes together. Again, you can see, I wrote down the last answer on accident. Sorry about that. So, again, the radical terms behave in a similar way as the variables do. Okay, or the radicals, I mean. The radicals themselves behave similarly as the variables, all right? And you can see that they smush together here with the 3 in both of these cases here. Finally, you've got an invisible 1 in front of this radical, so it's similar to this one. You just got to remember that there's an invisible 1 there. So 1 times 4 is 4. Outside times outside, 1 times 4 gives us the 4. Inside times inside gives me 55. Okay, and there you go. Same thing over here. The invisible 1 times 4 is 4. And then x squared times x to the 5th, you get x to the 7th. So again, once again, you can't say it enough here. The variables are similar to the radicals, the insides of the radicals, and then the outside parts of the radicals are similar to the coefficients. A very close connection there that really helps us because we've done these problems over here on the right-hand side so many times that seeing how similar those problems are to the problems on the left, it really helps. Okay, let's now use that knowledge now to, as I get a clean sheet of paper right here, to do these problems here when we have to rationalize the denominator. Whenever you rationalize the denominator, you guys, you always have to multiply the top and the bottom of the fraction by the same amount, okay, in order to keep it still equivalent or equal to the original problem. We're not supposed to change what it's equal to. We just change how it's written. It's still got to be equal to the original problem. So what do you multiply by? Well, Whenever you have just a square root, and it'll be different for cube roots and higher roots, but for square roots, just multiply by the same radical. And that should get the job done, and I'll show you why. Okay, if you multiply by the same radical, if you multiply a radical by another radical, sorry, let me back up. If you multiply a square root radical by another square root radical that's exactly the same, look at what happens. Isn't that equal to 3 right there? And I did this right because I know that inside times inside is supposed to stay inside, just like I just talked about. Okay, so that would be square root of 9. But we know that that is equal to 3. Okay, and we know that 3 is exactly what they asked for. They asked for a regular term with a whole number coefficient. It's okay if it doesn't have a variable, if there's none there, but no radical. And so we did it. We got a regular term with no radical. Fantastic. All right. So what then is the top? And then we'll be done here. Okay, so still got to multiply that top by the same thing. Again, inside times inside stays inside, and that's all you got to do. Okay. Let's try that again. This problem looks a little bit different, but just understand, and I showed this actually in something in the last section. We just didn't cover it yet. Let me go back to it and I'll show you. It says that if you've got a fraction inside of a radical, you can split it. You can split the numerator and denominator into 2 separate radicals and make a new fraction out of that. Just remember that whatever the root is or whatever the index number is right here, it has to be the same index number here and here. So if this is a square root, then these will both be square roots. If this is a cube root, like we'll see later, these have both got to be cube roots. Okay? So with that in mind, and we got to do that first here. Don't do that other thing that I just showed you without doing this first, because you got to know what your denominator is first with the radical surrounding it. All right? So do this first, split it apart, and then do what I showed you over here. What was that? Well, if you've got a square root on the bottom, just multiply by the same square root. And why does that work? It's because the bottom is now going to be, again, inside times inside stays inside. Okay. Now remember, in all of the sections here from 7.2 to 7.5, all 4 of those sections, the square root and the fourth root and all the even-rooted radicals, we can assume that the variables are positive, so you don't need the absolute value. So back in 7.1, this would have been absolute value of x. But now you can just say that it's equal to x, because that is the square root of x squared. Okay. All right. But yeah, 7.2, 7.3, 7.4, and 7.5, all 4 of those sections, you can assume that the variables are positive. Okay, so you don't need the absolute value bars. How about on the top here? If we multiply inside times inside, I get square root of 6x. And we did it. We made the denominator into a normal term, normal monomial term with no radical, not a radical term. Okay, now here's where things change up a little bit. All right, if you've got a cube root, you guys, you might be thinking, oh, hey, why don't we just do the same thing? No, you can't just do the same thing. First of all, let me make it clear. You have to, if you've got a cube root, you got to multiply by another cube root. You can't do a cube root times a square root. Okay, whenever you multiply 2 radical terms together, they have to be the same index number. They have to be. And so you got to multiply by the cube root of something. But if you multiply by the cube root of 5, you guys, what are you going to end up getting? You're going to end up getting the cube root of, look up here, cube root of 25. But the problem is that that's not equal to just a normal number with no radical. No. Okay, the square root of 25 would work, which is why if this was a square root of 5, then multiplying by a square root of 5 would have worked. But since it's a cube root, it's a totally different story. So when you have a higher root besides a square root, you guys, such as a cube root or a fourth root or anything higher than that, here's what I want you to do. All right, you've got 5 to start out, right? What you got to do is you got to say to yourself, okay, what could I multiply 5 by in order to get one of these numbers. Because these are the numbers that when you multiply, you're going to get a radical with one of these under it. And if you get a radical with one of these under it, assuming it's a cube root, which this problem will be, if you get one of these underneath that radical, the radical is going to go away because you're going to be able to evaluate it. It's a perfect cube underneath a cube root. Perfect cube underneath a cube root is just like a perfect square underneath a square root. You can evaluate it and make that radical go away. We've seen it so many times. Perfect square underneath a square root, the radical goes away. All right. Perfect square, 16x to the fourth underneath the square root, the radical goes away. You want to get one of those perfect cube numbers underneath the cube root. So let me ask you this. 5 times what is equal to 1? Well, of course, that's not going to happen. But 5 times what is equal to 8? That doesn't work, does it? And you don't have something that'll work for that. 5 times what is 27? No, that doesn't work either. We're not looking for decimals here, you guys. No decimals, all right? I know you could find a decimal that would equal 27 when you multiply by 5. We're not looking for that. 5 times what is 64? No, that doesn't work either because 64 divided by 5 doesn't divide evenly. How about 5 times something equal to 125? Well, if you put 125 divided by 5 into your calculator, you guys, you'll get what? You'll get 25. And so that must mean that 5 times 25 is equal to 125. Why is that important? It's because that means that that's the missing number right there that'll work. Because if I multiply by cube root of 25, I get inside times inside is equal to inside. But that then leads to the cube root of 125, which is, what is the cube root of 125? It is equal to 5. So I did it. I got rid of the radical. All right. So you want to get a radical where you can evaluate it. A perfect cube underneath a cube root, a perfect square underneath the square root, for example. Those kinds of things. All right. But I got to multiply the top by the same thing to finish the problem off here. All right. But as we just learned a few minutes ago, let me show you the example again. When you have just a regular term times just a radical, it just smushes together, doesn't it? Same thing here. You've got a regular term 8 times just a radical, nothing in front of that radical. So it just smushes together here. All right. Nothing combines. You just get the 8 times the radical. Okay. Let's keep going here. By the way, one additional note. Can you cancel here? Not this time, all right? You're not allowed to cancel inside of a radical. Don't ever cancel inside of a radical when you're trying to cancel above and below a fraction. But if you do have a single radical term divided by a single regular term, which you will see a lot, and we'll see that coming up here, in fact, single radical term divided by single regular term, you are allowed to cancel the outside part of the radical with this single regular term down here. It's just that 8 and 5 don't cancel. If they did reduce, like if it was 10 and 5, for example, then you'd do that. Okay, then you'd go ahead and cancel. Again, we'll see that coming up here. All right, let's keep going. Once again, we got to split this, but remember when you split it, because it's a fraction inside the radical, that's why you got to split it again. But remember when you split it, you have to make sure that both radicals have the same index number as the original radical did. Cube root up here, a couple of cube roots down here. All right, then that then begs the question, after you split it apart, you're supposed to figure out what to multiply by. It has to be a cube root because this one is. Got to be the same index number when you multiply. So again, let's ask the question one more time. We want to end up with one of these numbers here. So 3 times what is equal to 1? No, that's not going to work. 3 times what is equal to 8? No, that's not going to work. 3 times what is equal to 27? No, that's going to work. Isn't it true that 3 times 9 is equal to 27? And so because 27 is a good number here, multiplying by 9 will get us to where we want to go. All right. So on the bottom, I get the cube root of 27, which is 3, isn't it? But then I have to multiply the top by the same thing. Okay. And I get Inside times inside is cube root of 18. And there you go. Okay. All right, let's do that again now that we have another cube root. But this time I've got a variable in there. All right, now, when you figure out what you got to multiply by, you guys, if you have a coefficient and a variable too, all right, you got to look at those two things separately and figure out what to multiply by. If there was another variable, then you'd have to do three different things, all right? But here, there's just the two things. So here's what you do. You got to have a cube root again, all right, since the original radical was cube root. Then, looking at the 4 first, you guys. Let's go back to the list. Looking at the 4 first, all right? What can I multiply the 4 by in order to get something on this list? Well, 4 times 2 is 8, right? So that'll do it. So I'll put a 2 in there so that when I multiply it, I'll get an 8 in the answer. But I still got to deal with that x squared there. All right, x squared is not going to cut it. All right, that is not going to make the radical go away. These are the things that are going to make the radical go away when you combine it with the 8, which I forgot to write. Right there it is, right there. I know I'm going to have the 8 in there, 4 times 2. But what do I got to multiply x squared by so that I'll have something, as far as the variable is concerned, I'll have something in here that'll also be a perfect cube. Well, isn't it true that x squared times x would give me the x to the third right here? So you just got to figure out what to multiply by to get one of these things, preferably the smallest thing that you possibly can get. All right. And so that's why multiplying by x will give me the smallest thing there that I can possibly get, which is x to the third. Okay. If this had been x to the fourth, then you'd want to multiply by x to the second so that you could get x to the sixth, for example. All right. Because you need each part here, not just one part, but each part here. Each part needs to be on this list. If each part is on the list, then as we saw back in 7.1, not just there though, but in some other sections as well in this chapter, if each part is on the list, then you can evaluate it and make the radical go away. All right, so what do we get here? That is going to be equal to 2x, isn't it? On the bottom there. Okay, but I got to multiply the top by the same thing. And once again, when you have a regular term times just a radical, you get the two things just smushed together like that. Okay? And so we're done with the exception of the fact that, remember I said a couple of problems back that if you have a single radical term divided by a single regular term, we talked about this up here in problem C up here. If you've got a radical term divided by a regular term, you can cancel, but you have to cancel with the outside parts right here, not inside the radical. You can't do that. So don't cancel 2 and 2 or x and x. No. But you can cancel the 10 and the 2. Just in the same way you would if the radical wasn't even here. If you had 10 divided by 2x, how would you cancel that? You just do it the same way. You cancel the 10 and the 2, you get 5 and 1. And so the final answer is going to be 5 cube root of 2x over just x now. The 10 and the 2 reduced. And there you go. All right. All right, now we're going to jump all the way up to the 5th root of something. Okay. But it's the same idea, though. Don't be intimidated by the fact that that's a 5th root. Now, I know we don't do those very often. We did a few of them in a couple sections back. But because it's the 5th root, we look at the perfect 5th powers, and we do the same thing that we did with the cube roots. Okay? We look at each one of these things one at a time. The 8, and then each variable. The coefficient, and then each variable, you guys. Let me zoom in a little bit. And you just take one at a time and you say, okay, 8 times what is a 5th power? Okay, 8 times what is equal to 1? Well, that's not going to work, of course. 1's smaller than 8. But 8 times what is 32? It's 4, right? Okay. 8 times what, or pardon me, x times what is going to be equal to one of these? Well, x times x to the 4th is equal to x to the fifth, so that'll work, won't it? 1 plus 4 here on the exponents gives me x to the fifth. And then y to the third times what is going to be equal to one of these, assuming that these are y's now. Well, wouldn't y to the third times y squared give you y to the fifth right here? Same exponent. Can be a different letters as long as it's the same exponent. And so this is the thing that you multiply by, and it's going to be equal to what? Let's take a look. This is going to be equal to the fifth root of 32x5y5. Okay. What is the and does that make the radical go away? It sure does, you guys, because the fifth root of 32x5y5, isn't that equal to 2xy? Okay, because if you took this entire thing to the fifth power right here, it would be equal to that. And so that is the fifth root right there. Now, we got to multiply the top by the same thing right there. And so once again, when you have a regular term times just a radical, it just all smushes together like this. Let me finish writing that out there. Okay. All right, so we did it. We got a regular term here on the bottom, 2xy, no radical. But remember what we said. If you can reduce the outside parts right here, go ahead and do that to finish off the problem. Okay, so what can I reduce here? And again, pretend like the radical is not even there, and then ask yourself, could I reduce these two things in the normal way that I would have if I just had these two terms without the radical here? Yeah, you can. You can cancel the x's. Since they're the same exponent, it just becomes 1 and 1. And then the y squared and the y, you do 2 minus 1. Like we've done so many times this semester when you got a single term over a single term. Okay, you subtract the exponents. You get y to the first over 1. So what does all this end up being after you simplify these terms that you just reduced? You get 3y, radical's still there. We just reduced the other parts. 3y times the radical still. And then the bottom is just 2 now. 2 times 1 times 1. All right. And so there we go. All right. So that's what you do to rationalize the denominator. Again, just a review here. All right. If you've got square root on the bottom, you just multiply by the same radical, and that'll do just fine. Square root of x times square root of x. Square root of 3. Let me zoom out. Square root of 3 times square root of 3. But when it's a higher root, such as cube root, okay, or even fifth root, and yes, it counts for fourth root as well, any higher root than a square root, you got to look at the perfect cubes or the perfect fourth powers, or in this case, the perfect fifth powers, and see what you can multiply by to get it equal to one of those things so that you can then evaluate that root. Evaluate that fifth root right there in this case, or a cube root, okay, whatever it may be. All right, so please try, with that in mind, please try 1 through 4 down here. All right. Remember to split apart this thing right here when you got a fraction inside of a radical. Split it first before you decide what to multiply by. Okay, go ahead and hit the play button when you're ready. Okay, so in number 1, since this is a square root, just multiply by the same square root. You should be good. All right, we know that the bottom now is what? The bottom is now going to be inside times inside gives me 9y squared on the inside, which then becomes 3y, doesn't it? Okay. The top, you multiply by the same thing. It just smushes together. All right. And then the 12 and the 3 reduce because, again, single radical term divided by a single regular term, you're allowed to reduce the outside parts. All right, like we talked about. And so our final answer is just what you see right there. Let me move that up a little bit. There we go. All right. How about number 2? Number 2, let me just set it up here. There we go. we have to multiply. We can't just multiply by the same radical when it's a cube root or a higher index, okay, than that. Only for square roots should you do that. So what could I multiply 4 by in order to get something that's on the perfect square list? Okay, or the perfect cube list, since it's cube root. Well, isn't it true that I can multiply by 2 and get 8, which is on the list? Okay. Are there other numbers you could have multiplied by? Yeah, but this is the smallest one, so that's best. Okay. If you'd multiply by a higher thing, then you would have ended up with a radical on the top at the end of the problem that you would have had to simplify, because the directions say to simplify your radicals in the answer. But if I multiply by this, it's going to be easier because I won't have to worry about simplifying my radical at the end. I just get cube root of 6 over this cube root of 8 right here, which becomes 2, doesn't it, when I evaluate it? It's just equal to 2. Okay. Number 3. If I split that apart right there, I get this right here that you see. And as you can see here, we got a couple of variables in here. There's no coefficient other than an invisible 1. And when it's 1, you don't have to worry about doing that one. But you do need to do each variable. So again, you ask yourself, since it's a cube root, what could I multiply by to get one of those variables on the perfect cube list? Which is what? Which is x to the third and x to the sixth and so on, one of those. Well, couldn't I multiply x times x squared to get x to the third? And couldn't I multiply y to the second times y in order to get y to the third? Okay, you see that right there. That would give you x to the third, y to the third. All right, and then what is that? Why is that going to work? It's because that is both of those parts in there are perfect cubes. As long as each part is a perfect cube or a perfect square in a square root situation, then you can evaluate it and get rid of the radical, and we get xy on the bottom. On the top, you multiply the inside times the inside, and you get what you see right there. Okay, so that is number 3. Okay, finally, number 4. Bring that up. There we go. Why did I multiply by 2x to the third? It's because we know that 32 is one of the numbers on the perfect fifth power list, which is what we're looking at, since this is a fifth root. So 16 times 2 will give me that 32 that I want. All right. And then we know that x squared times x to the third is going to give me something. What is on the perfect fifth power list? It's x to the fifth, x to the 10th, those types of things right there, right? And so we know that multiplying by x to the third will give me x to the fifth. So now each of the two parts in here is a perfect fifth power, which we need it to be in order to evaluate a fifth root. What is this equal to right here, this entire radical? It's going to be equal to 2x right here, okay? And so we obviously 2x is just a normal term, okay, without a radical. That's what we wanted. The top just smushes together, and then we can cancel the outside parts like we talked about. And so our final answer is all the way down here. Okay, let me zoom out a little bit for you. There we go. There it is right there. And that concludes the first part of this section. Okay, the second part of the section is going to be still rationalizing the denominator, but just a little bit different as far as what the denominator looks like. Okay, we'll look at that here in the back side of this worksheet. All right, but this is what you do though when the bottom of your fraction has just one radical term. All right, not two terms like we'll see coming up, but just one radical term. All right. All right, now as we flip over to the back side, okay, here are the problems that now have two terms in the denominator, okay? And the way they're done is completely different. Here's why. Take a look at this first problem. It's got a square root. All right. In fact, all these problems that have two terms in the denominator, separated by either addition or subtraction here, addition here, for example, all of them will have square roots only. You won't have any cube roots or fourth roots. In fact, what I'm about to show you would not work unless it was only square roots in the denominator. But that's what it's going to be, so that's fine. Anyway, what if I had just multiplied by square root of 10 right here? Okay. The problem with that is that when you multiply by a denominator that has more than one term in it, you are supposed to, as we've seen before in the past, you're supposed to distribute it. Now, if I multiply square root of 10 times square root of 10, that's great. All right. That would be equal to square root of 100. All right. Which is, going to be equal to 10, and then the radical's gone, and so you think, oh, hey, that's great, all right? But then the problem is that when you distribute to the other part here, though, you then end up getting negative 2 times square root of 10, and so the square root of 10 ends up reappearing here in the second part, even though it would have disappeared from the first part here, okay? And so that's why you can't do, and that's why I'm going to pull up my eraser right here, and I'm going to erase this, because that is not going to work. All right, something similar to that is going to work. All right. Here's what we do. I'm going to pull out a separate piece of scratch paper here just to show you this. Again, you don't have to write this down, but because you're going to be writing it down eventually on the big paper here that we're looking at. But all of my denominators that I have in all 5 of these problems are listed right here. Okay. Don't include that there. I wrote that a little bit too soon to pretend like that's not there. That's square root of 11. I'm going to write it eventually, though, but don't pretend like that's not there. So we've got these 5 things here, okay? And we're going to use this formula that we saw back in Chapter 5 when we learned how to factor 2 terms, okay? We are going to have, for example, if you've got a subtraction in your denominator, you're going to multiply by the same thing, but you're going to change the middle to addition. Okay? And then if it was addition, this is the second denominator in the second problem you have on the current worksheet. Problem H, I believe it is. Yes, problem H. All right, so in that case, you'd multiply by square root of 11 minus square root of 5. Okay, why would you do this? Why would you multiply by the same thing except for the middle changes from either addition to subtraction or subtraction to addition? Why would you do something like that? It's because according to this formula, if you've got A minus B, A plus B, okay, in other words, the two things are the same, except for, once again, one of them's got the minus and one of them's got the plus. You can see that that's exactly what's going on here in G and H, okay? What's going to end up happening is that, according to the formula, you're supposed to square the A, which is the square root of 10. As you can see there, the A is the square root of 10 right here, okay? So square root of 10 squared. That's what they're telling us to do. And then what's the B here? The B is 2, right? And so we're supposed to square the 2. What ends up happening, you guys, and bring down that minus that's in between that right there. Bring that down, bring all this down. But what happens here is that now, because you're squaring both of these things, if either one or both of these things has a square root in it, the square root is going to go away. All right? Look at this over here. Square root of 10 squared. Okay, let's take a look at that for a minute. Square root of 10 squared is the same thing as multiplying the square root of 10 twice, of course. Okay, we're going to look at a shortcut in just a second, don't worry. But we learned that square root of 10 times square root of 10 is equal to square root of 100. Inside times inside is equal to the inside. All right, stays inside. But we know that the square root of 100 also is equal to 10. So what's the shortcut? Instead of having to write all this out every time, when you square a square root, okay, not a cube root or a fourth root, but when you square a square root, okay, essentially the square root disappears and you just get the number on the inside. You can see that here. This proves it. Okay, just so long as that is not a... as long as that's not a negative underneath there, because you can't square something that isn't even a real number to begin with. And we know that the square root of a negative number is not a real number. Okay. When we talk about imaginary numbers later, we'll talk about how to deal with that. But for now, when you square something, when you square a square root, as long as it's not a negative underneath the radical, it's just going to be equal to that same number that's underneath the radical. Basically, the square and the radical cancel each other out, in other words. Okay? So that means that this right here is 10. But this right here is 4, isn't it? Isn't 2 squared equal to 4? No radical there, okay? So it's going to, you just square it in the normal way. And so your final denominator there, if you multiply by square root of 10 plus 2, is going to be equal to 6, okay? So let's go ahead and write that down, all right? We're going to multiply by 10, square root of 10 plus 2, okay? Put that in brackets because it's got more than one term in it. That's why I had it in brackets in my scratch piece of paper here. Okay, also put this in brackets to remind you that, hey, I've got to treat that like there's a bracket there because there's 2 terms there. Okay, let me zoom in on this a little bit. But whatever you multiply the bottom by, you have to multiply the top by the same exact thing. Okay, we'll get to the numerator in just a moment. As we just found out, the bottom is equal to square root of 10 squared. I'm just rewriting this so you have it on the paper. Minus 2 squared. And as we know, that is going to be equal to 10 minus 4, which is 6. Okay? And we did it. We turned the denominator into a regular term that without a radical, just like on the front side of the worksheet. Okay? Had to do a little bit more work to get there, but we did it. Okay, now on the top, they do want us to multiply out the numerators. That's why it says the final answer cannot have any brackets in your numerator. They want you to actually, when you got a term times a bracket, for example, they want you to distribute that out so there won't be any brackets there anymore. Okay, so if I distribute, now remember, when you have 2 terms inside of a bracket separated by either addition or subtraction, and then you got a single term being multiplied by it, like we've done so many times, especially in equations, but not even in this case as well, similar thing, single term times a bracket with 2 terms in it, we distribute. So 17 times radical 10, a regular term times a radical, it just smashes together, 17 rad 10, like that, okay? And then 17 times 2 is positive 34. So just like always, if it's positive, you got to put the plus there when you're distributing. You got to have pluses and minuses in between your answers when you're distributing. Okay? And that's it. All right? We did it. All right. So they just wanted to rationalize the denominator, get rid of the brackets in the numerator. Sometimes they might ask you to simplify your radicals in your answer, but square root of 10 is already completely simplified. You can't break that down anymore, and so that's why we are done with that. Okay. Problem H. Again, going back to that scratch piece of paper that I had. I know that my denominator is rad 11 plus rad 5. So in order to be able to use this formula here, I want to be able to multiply by rad 11 minus rad 5. Because what's going to happen is that I'm going to get the first term in each bracket. According to this formula here, the first term in each bracket gets squared. You put a minus in between like the formula says up here. Bring that down. And then you take the second term in each bracket and you square that. And what did we just learn, you guys, about squaring a square root? Squaring a square root is going to be equal to just the number underneath the radical. Okay, so square root of 11 squared is 11. Square root of 5 squared is 5. And then remember, exponents come before subtraction. So we do subtraction after we do the exponents. And just a coincidence here, the denominator ends up being the same as the previous problem. Okay, 6. All right. Why is it that this one was not equal to 2, even though this one was equal to 11 and this one was equal to 5? It's because this was not a square root, you guys. This is just 2. So you just do 2 squared like you normally would, and so that's 4. Just be careful of that, all right? When you're squaring a square root, it's just equal to the number on the inside. But when you're squaring a normal number, then you just square it like you normally would. 2 times 2 is equal to 4. Okay, so just watch out for that. It's an easy mistake to make. Okay, and so let's write that down here. Square root of 11 minus square root of 5. Again, it's got 2 terms, and so we're going to put a bracket around that. This also has 2 terms over here, and so we are going to bracket that as well. Okay, just to remind us that I've got to treat it as if there's a bracket there. But I got to multiply the top by the same thing I'm multiplying the bottom by. Okay. So as we just found out, the top, or pardon me, the bottom is equal to square root of 11 squared minus square root of 5 squared. I'm just transferring this from the scratch paper over to here, so we'll have it here. And that ends up again being equal to 11 minus 5, which is 6. Okay. Now, how about the top? What's going on with that? Well, since this has 2 terms here, unlike the last problem where you had just 1 term in the top, so you didn't have to bracket that when it's a single term and you're multiplying it by something. Okay, but if it's got more than 1 term and you're multiplying it by something, and we always have to multiply the entire numerator by whatever you're multiplying the numerator by. Okay. So if it's got more than 1 term, bracket that to remind you that you got to multiply the whole thing, okay, and treat it as if there's a bracket there. And so I put the bracket there to remind us that it's as if there was an invisible bracket there, okay, when we're multiplying it by something. So I put it there to make sure that we can clearly see that now, okay, now that I am multiplying. Okay, so now, how do I multiply when I have 2 terms times 2 terms? Okay, well, as we've seen many times going all the way back to chapter 5, okay, when you got 2 terms times 2 terms, what do we always do? Okay, just like this problem back in section 5.2, 2 terms times 2 terms in each bracket being multiplied here, you just do the 4 multiplications that you would normally do in that case. Okay. So same thing here. Let's be careful this time though, because we got radicals. Square root of 11 times square root of 11. Well, isn't that the same thing as squaring the square root of 11? Okay. You could do it one of 2 ways, and either way it's going to come out the same answer. Okay. If you are multiplying the same radical twice here, I'm just going to pull it off to the side here. If I multiply square root of 11 times square root of 11, remember, when you multiply a radical term times another radical term, you multiply inside times inside, and that stays inside. And then that would be equal to 11, because I can evaluate that, can't I? Since there's a perfect square underneath there, I can actually... you're supposed to simplify your radical here after you do that, but since it's a perfect square, simplifying it is the same thing as evaluating it. When everything on the inside, in this case 121, is a perfect square, all right? You just evaluate it, all right? But wouldn't it have been easier to just say, oh, hey, this is the same thing as square root of 11 squared, and I know that when I square a square root, it's equal to 11. So you don't even need to write down this 121 thing here. All right, you know that when you multiply a square root, and I'm not talking about when you got a term in front of the radicals. That's different, because then you got to deal with that separately. But if it's just a radical times another radical that's exactly the same radical, and they're both square roots, not cube roots, but square roots. Okay, it's just like you're squaring the square root, and so you don't need to write down this additional step here. You can just say, oh, hey, that's 11. All right. And so this first part here is 11. Then the next one here, square root of 11 times square root of 5. Remember, you got to look at the signs in front of each term too. We got positive times negative, so that's going to be negative something. All right, but negative what? In other words, it's like having a positive 1 times a negative 1. Because theoretically, you're supposed to multiply outside times outside as well. But if there's no coefficient, or there's no number, no term in front of each bracket there, if there's no term in front of each radical, excuse me, you don't really need to multiply it. You just need to know that it's positive times negative. All right, that's why I brought down the negative right there. Okay. But it would be the same thing as doing 1 times negative 1. You'd have a negative 1 right here and then a radical after that. It's the same thing, okay, as just putting the minus down there with the radical after that. And speaking of that radical, what would go inside of that? Well, you're supposed to do inside times inside, okay? So we do inside times inside, and then if there's no terms on the outside of the two radicals, just make sure you've got the correct sign by looking at the front of each radical. All right, positive times negative gives me the negative. Same exact multiplication here on this one. All right, square root of 11 times negative square root of 5. So positive times negative is negative again. Inside times inside is going to give me 55 on the inside. And then finally, negative times negative is positive, so put down that plus there. You always got to have pluses or minuses in between these answers here when you do these 4 multiplications, just like we did in 5.2. And then, as you guys know, if you multiply a radical times the same exact radical, assuming they're square root radicals, okay, it's just like you're squaring that square root. And so the answer there would simply be 5, okay? Now, there's one additional thing that I need you to do on this problem, okay? We did clear out the brackets in the numerator like they asked us to, but there is one other thing that they want us to do. After you multiply out the brackets, I wrote it down up here, after you multiply out the brackets in the numerator, simplify the radical terms if possible, then combine like terms. Simplify the radical terms if possible, and then combine like terms. Are these radical terms already simplified? Yes, they are, but just double check, okay? Then after that, assuming that they already are, and if they're not, do that first after you multiply out the brackets. Simplify those radicals first if they're not already, but then combine like terms. Okay, when you got a bunch of regular terms like 11 and 5 and a bunch of radical terms like these two radical terms in the middle, when you got a bunch of those being added and subtracted together here, the way you combine like terms is just like we've learned, okay, where you can combine the regular terms if they're like terms. We know that 11 plus 5 is 16. And we know that we can combine radical terms that are being added or subtracted together like these are, okay? If they are the same radical, we can do that, and they are the same radical. So this is negative 1 minus 1 right here. When we combine these two together, negative 1 minus 1 would be negative 2, with the radical staying the same, okay? So combine the regular terms together if you can, and we can with 11 and 5, and then combine the radical terms together if you can, and we are able to here because they are the same radical. Again, this is when you got a bunch of terms being added and subtracted, like we do here, after you're done multiplying out the brackets up here. Okay. Now this is a completely acceptable answer here. Let me just clean it up here a little bit. This is a completely acceptable answer. All right. But the textbook, if you're comparing your answers with what the textbook is writing, and I'm going to go and circle this because, like I said, if you give this as your answer, that's fine. Okay, you multiply out your brackets, you combine any like terms in the numerator after you've simplified any radicals, all right, then that's fine. Okay, but the textbook likes to do this. It likes to take the numerator, and if you've got a radical term in your numerator, ignore the radical part. But otherwise, factor out the GCF out of the numerator. Factor the GCF. So in other words, just look at the 16 and the minus 2. What's the GCF of that? That would be 2, wouldn't it? And if I factor that out, I would get 2 times 8 is 16. And then, isn't it true that 2 times negative rad 55 would be equal to negative 2 rad 55? And isn't that what we do when we factor out the GCF? We have to figure out what the missing parts are inside of the bracket here to make it still equal to the numerator here. Why did I do this? Why does the textbook like to do this? They like to do it because then they can according to our canceling rules that we've learned a number of times, we can then realize that we have a couple of green ones here, one on top, one on the bottom, that can cancel. The 2 and the 6 can cancel, okay, and become what? It can become 8 minus rad 55 over 3 now, okay? Because the 2 and the 6 become 1 and 3. So this is what the book would have done if you're comparing your answers with the back of the book. But this is also an acceptable answer. So either one of these answers is acceptable. But please, you guys, please do not cancel the 16 and the 6 or the 2 and the 6, all right? Because this is 2 terms. You're not allowed to do that. Remember, when you have 2 terms, you have to factor, or at least try to, and then identify your factors before you can even think about canceling. We learned that in Chapter 6, and that's still true now. Okay. Why did we not do all of this back in the last problem, by the way? Okay, let's take a look at both of those problems together. It's because there were no like terms to combine. The radicals were already simplified. And yes, I could have factored out the 17 here from the 17 and the 34, but I didn't do that because I already knew that the 17 and the 6 were not going to cancel. So I didn't bother to show you that there, only because I already knew it wasn't going to do anything. And remember that last step where you factor out the GCF, that is optional anyway. It's just if you like to compare your answers to the book. But the thing that is mandatory is to combine your like terms after you simplify that radical. Well, there are no like terms and the radical was simplified. That's why I circled this. But over here, I went a little bit further with it. That was the difference. Okay, just wanted to make sure there was no confusion there. One more here. Okay, problem I. And again, looking at our... So going back to the scratch piece of paper, we can see that 5 rad 2 minus 3 rad 5, we have to multiply by the same thing as we did in the first 2 problems, but we have to change the middle, right? And so we get what here? We get the first term is squared, just like in the first couple problems. The second term is squared in each bracket, like that. And then you put a minus in between that. Now, we got to be careful about how we square when we have not just a radical inside the bracket, but the term in front of it here as well. Okay, the way to do that is you still square the square root, and you know that when you square the square root of 2, it's going to be equal to 2, right? Okay, so that's going to be part of it here, but you also square the 5, okay? So 5 squared would be 25, and then you multiply those 2 numbers to get this, what this thing is equal to here. Okay, so 5 squared, square root of 2 squared, that would be 25 and 2. All right, bring over the minus sign. Okay, don't subtract yet. We still got to do some multiplication here. Over here, it's the same thing. You still do square root of 5 squared, which is 5. Okay, but you have to square the 3, which is 9. And so what do we get here? We get, multiply before you subtract, we get 50 and 45. Okay? And that's why the final denominator here is going to be equal to 5. All right? So if you've got an outside part there, outside of the radical, and you're squaring that entire radical term, which you're supposed to do here, all right? That's why I put it in the brackets here. Make sure to square that outside part as well. All right, just like I just did. So let me transfer all of that back over to here. Just give me a moment to write that down. And so we're going to get those 2 things being squared right there. 25 times 2 minus 9 times 5. 50 minus 45 is what that's equal to. And that ultimately leads to what here? It leads to a denominator that is equal to 5. Okay, but the numerator is a whole different thing, you guys. All right. Actually, it's not that bad because there's only a single term on the original numerator. Okay, I was thinking of the last problem there. This one's not too bad. Okay, do not, and I want to remind you something here, do not, before you multiply out the numerator, check to see if you can cancel anything in the numerator and denominator. Okay? We didn't do that in the previous two problems because I knew that nothing in these two brackets would cancel with the 6 that I got from my denominator. I knew that. All right? It's just a couple of brackets with two terms in it. It's not going to cancel with the 6. Same thing over here. The 17 was not going to cancel with the 6 as we talked about earlier. And so I knew that I can just go ahead and multiply that out. But it says, before multiplying out the numerator and getting rid of the brackets there, just check that first to see if anything cancels. You know that what we're supposed to do is multiply 35 times this bracket, right? But before you do that, what I'm saying here is go ahead and realize that when you got a term times a bracket with more than one term in the bracket, that's a green one right there being multiplied by a red one. All right. The bottom here is now green after we figured out what it was equal to. Okay, so figure out what the denominator is equal to. See if that new denominator cancels with anything on the top before you actually clear out your brackets. It makes things easier because this time what happens? The 35 and 5 do cancel. Remember, you're allowed to cancel green with green. All right, so I can do that. And I get what here? I get 7 times the bracket, but now the denominator is equal to 1. And so there's not even a denominator anymore. All right, so it just makes things easier now. Now all you got to do is you just multiply out these this bracket here. They still want you to multiply out the numerator, so go ahead and do that. And then we'll be done. Okay. 7 times the radical term, you multiply 7 times 5, the outside parts. And when there's only one radical in the multiplication, that just comes down. We saw that a number of times in 7.4 and even in 7.3. Multiply 7 times 3 rad 5. Positive times positive is positive, so I bring down the plus. 7 times 3 on the outside parts is equal to 21. That stays outside. And then again, the radical doesn't have another radical being multiplied by it, okay, because the 7 didn't have a radical. And so the rad 5 just drops down. Since the radicals are... officially, this is still the numerator because the denominator is 1. You just don't have to write the denominator when it's 1. So officially, after you clear out your parentheses, check to see if there's any radicals that need to be simplified or any like terms to combine. But you can see here that the radicals are already simplified, and these are not like terms because one has rad 2 in it and one has rad 5 in it. Remember, terms are separated by what, you guys? It's separated by a plus or a minus. So there's just 2 terms here. Both are radical terms, but they don't have the same radical. Okay? All right. So please try 5 and 6 right now, keeping in mind that what you need to do is multiply by the appropriate thing here. I'll let you fill this in and figure it out. These are the 2 denominators you still need to do here. And then finish off the problem using the guidelines we talked about. Okay? So go ahead and try those 2. And this should not say J and K. This should say 5 and 6. Okay, those are the 2 problems. Those are the 2 problems that we're doing here. Okay, so do 5 and 6 and then hit the play button and we'll take a look at the answers. Okay, let's take a look at number 5 right here. Again, we need to multiply by what here? Let's take a look. 3 rad 6 minus rad 5. So we need to change it to plus when we figure out what we're multiplying by. That leads to what? That leads to squaring the first term and the last term of each bracket, putting the minus in between. And like we talked about in the last problem up here, okay, we need to do what when we have an outside part of the radical term? We need to do 3 squared is 9. We also square the square root like usual, and so that would give me the 6. Okay. For this one, there is no outside part, so you just got to square the square root, just like we did up here in the first 2 problems, and so that would just be 5. We still have that minus sign in between all of that, like that. And so we end up with what? We end up with 54 minus 5 is, again, multiplication before subtraction. So the final denominator there will be 49. Okay, so let's transfer all of that information back over to the current problem that we're looking at. You see we got 49 right there. Now how did I get this numerator here? Well, since you got two terms in the numerator and two terms that you're multiplying by, that's the normal thing where you got to end up with 4 multiplications here. Let me talk about that. This first one here, remember, when you multiply a radical term times another radical term and they both have outside parts to it, what do? Outside times outside stays outside, so that's the 6. Inside times inside stays inside, and so that would give you the 36 on the inside. But we know that square root of 36 is equal to 6, okay? And so that's why in the next step here, I'm going to just say that whole thing right there, the first term in the numerator is just going to be 36 right here, okay? I'm aware of that there, and that's all part of simplifying your radicals after you multiply out your brackets. But yeah, that's what's going to happen right there. All right, we're going to simplify our radical. That's where the 6 comes from. Okay, if you're simplifying a square root with just perfect squares on the inside, it just is the same thing as evaluating it, getting rid of the radical. All right, because you can. Multiplying the rest of these out here. Okay, these two right here, outside times outside, 2 times 1 is 2. Inside times inside is 6 times 5, it goes inside, 30. All right. And then same thing on the last two here, or actually the next one. We got 1 times 3 on the outside is 3. 5 times 6 on the inside, it goes inside, and that's why the 30 is on the inside. Radical times radical. Radical times the same radical with nothing on the outside. You just have to square that. Square the square root, and that's equal to 5. Positive times positive is positive, and that's why you got the plus right there. All right, so again, look at the front of each radical term or the front of each term to figure out what the sign of each one of these things is in front of each of the 4 answers. We know that we already got 49 on the bottom. We already figured that out. Okay, and then after you multiply out your numerators, simplifying your radicals that you have, including the 36. So that gives me 6 times 6 equal to 36. Okay, then combine your like terms there. The 36 and the 5 become 41. These two radical terms, because they're the same radical, I can combine those. 2 plus 3 is 5. Radical stays the same. All the same stuff that we talked about in section, this last section 7.4, where you can add and subtract radical terms. Okay, the radical stays the same. Okay. No, I cannot, and not that it's mandatory anyway, like I promised you, but no, I cannot factor anything out of 41 and 5, so you can't do that thing where you do the GCF there. All right, so you can circle this, and that's it for problem number 5. All right. Number 6. All right, well, as we see here on the scratch piece of paper again, okay, when you have 7 plus, and I may have a little misprint here, let me fix that. If I have rad 7 plus rad 3, I need to multiply that by rad 7 minus rad 3, and that gives me squaring both the first and the last term. What are these things equal to, you guys? When you square a square root with nothing outside the square root this time, there's not like a 3 like there was on the last one. It's just a square root. It's just equal to the 7. And the other one's in the same way. It's equal to the 3. The minus then is still in between that. We subtract after we do the exponents, and we get 4. So the denominator, the new denominator, is now going to be 4. Okay. As you see right there. Again, like I told you before, do not multiply out the numerator until you are certain that nothing cancels, because this time, this is one of those cases where something will cancel. All right. And so, in particular, you want to do that when the original numerator is a single term, because then it might cancel with the brand new single term that you get when you figure out what the denominator is. All right, we saw that in problem I just a few minutes ago, and we see it now here. Okay. And so I did that, and it gave me this right here. All right. And then you just have to multiply out that brand new numerator there. Okay, the denominator is now 1, so that's why I didn't write it out. But you multiply that out, and you get this right here. There's no radicals to simplify, and there's no like terms here, and so that's why I circled it. Okay, so if you can cancel before multiplying out the numerator, do so. Do so if you can cancel before that. Otherwise, multiply out the numerators. All right. Then simplify any radicals that you have after you multiply out the numerators and get rid of the brackets on top there. Okay. Simplify your radicals and then combine like terms. Okay. Sometimes you won't have any like terms, and sometimes all the radicals will already be simplified, but at least check it to see, okay, if you can do any of that. All right. So that concludes the Rationalizing the Denominator discussion here in section 7.5. As usual, let me know if you have any questions. You enjoy your day.